Now it's my pleasure to announce the talk of Professor Dr. Marc Toussaint. He is a professor for AI and robotics at the TU Berlin, and he's also the lead of the Learning and Intelligent Systems Lab here at the TU Berlin. And we will now give him a great round of applause for his talk about planning in the age of learning.
Okay. Cool. I never had an applause like that, so that's a cool experience. Thanks. And this, thanks for the invitation. That actually sounds like a lot of fun, the whole like Bliss thing. So it's actually great that you initiated. Cool. So for today, I picked a pretty generic title. That's because some months ago I had no idea what I will talk about. So it's pretty generic, but it does express one thing, which is that I find planning an interesting topic. And it is especially interesting nowadays because there is so much advance in, machine learning and like training systems. And everybody just talks about you just train the system to predict anything, like transformers, anything, right? And so what's even the role of planning nowadays that you can just, take a transformer so to predict anything. And that's a bit the like general topic that I will also talk about, but then also much more specifically about robotics. So the talk might be just maybe 35 minutes, 40 minutes, something like that. It's not too long. So I invite many questions also later. Feel free to ask anything. And I organized it a bit like that. So I'm first going to start with some background, and the background will also include a discussion, like a motivation for me and like how I think about things, how I think about planning and these kind of things. And then there is a technical part where I just discuss one paper. I thought it's nice to just, talk about something more specific, learn something concretely, like how we use deep learning, whatever, to learn constraints. You'll see that's the technical part, and then conclude again with a bit bigger picture about this type of integration of planning and learning. So let's start with why should we even care about model-based planning? And I assume that the audience is pretty diverse here. There is quite some robotics parts also, maybe half of it or so, but I should start addressing like everybody. So why even care about model-based planning? And in a previous talk, I had a slide with all the arguments against it, but the slide was so large that I skipped it here. There's a ton of arguments against it, right? Because you need to assume models, they're all wrong, and it will never generalize and sim to real, and tons of arguments against it, but I'll skip them. So the argument for planning is, I think, generalization. And everybody in machine learning should find generalization like super interesting. But yeah, so if you think about generalization, like really trying to predict something completely outside the data distribution, there may be many different opinions about that, but I think one valid, and one is to think that, some kind of more complicated mechanisms like planning actually achieve that. And a trivial example I put here are chess engines. So I think it would be super boring if chess engines would be only trained by behavior cloning, only cloning humans. It would be super boring, the whole thing, right? But no, they're not. They're like much better than humans. They really can plan. They can generate, games that humans could never conceive of, that are completely confusing also for humans, right? They can really do amazing things. And chess is, I know, a kind of boring style of planning, but still it kind of like shows the cool stuff that planning can do. And yeah, so this is a bit the, the idea really, or the motivation for model-based planning, of course, generalization. And my stance is that, these kind of things that we call reasoning or inference, I had a time when I worked a lot on probabilistic inference methods and factor graphs and stuff, inference or planning, that all of these are like kind of things, mechanisms, procedures that allow you to really go beyond the data distribution. And I think not everybody might agree, and I might pick up that discussion again maybe sometime later, because nowadays people always say, but you could also train a language model to do the planning, right? And then people also say, and a language model could also go beyond the data distribution. And sometimes I'm lost, but actually, I think it doesn't even matter so much to debate about that. I think both of these are really interesting views, and I find it interesting enough to study, like really, planning methods. And from that perspective, I sometimes think about what is actually interesting architectures or algorithmic processes for, if you think about planning. And again, the typical machine learning thinking would be, what should I put into my neural architecture? And there's been interesting research on that. So, well, the first one would be, you don't need to put anything. You just take a feed-forward mechanism. Transformers are kind of feed-forward, right? Or you could argue that they're recurrent. But anyway, so one thing is maybe if you have enough data, you don't need to put any algorithmic priors into your architecture. Okay, there is some other kind of work that also actually try to plug in like reasoning mechanisms or inference mechanisms into like a PyTorch model of the full thing that you train end to end. So one of them is, for instance, called this value iteration networks. Some people, if Jürgen Schmidhuber would be here, he would say, you don't need to put any algorithmic priors. You know, LSTM can just learn any computer and therefore any planner. It's also like a stance. But then there is also like classical algorithms that I like to learn about. Actually, I find it interesting, like search and sampling, optimization methods. I work a lot with optimization, also probabilistic inference. And my general stance is that I think that we could have much more ideas actually to integrate these stuff, like also classical optimization methods, with modern like generative models. So, and I might mention the word generative model a bit more actually at the very, very end. Okay, so this was about the planning itself and generalization, and I'm totally for that. And the other, now a bit about robotics. There is not so many maybe roboticists here. So let me quickly talk about robotics and make it perhaps interesting also for some of you. So the kind of old-fashioned view of robotics, I think, is very robot-centric, which, yeah, it's just how it is. So I remember when some 15 years back, when machine learning from, if you were like a neurops person and then you went to a robotics person, you typically, the first thing is you used machine learning to learn the robot dynamics. So you learn something about the robot itself. And even, you know, describing robot dynamics is a big topic within robotics. And then also like making robots walk, which is called locomotion, or making robots to fly super high speed through some kind of like parkour or whatever, drones. So high speed racing, also many Mojoko benchmarks. All of this is kind of like only about the robot. And it's learning, you know, how the robot should move, how it should fly. So super robot centric. And that's all fine, but I actually think much more interesting is to not only look at the robot, but understand robotics really also as a research field that is very much about the environment, the interaction and manipulation with the environment. And for this audience, I had the idea to, is this me? Yeah, I don't know. I had the idea to make an analogy to computer vision. So imagine computer vision would only be about the camera and the rays. That's kind of like boring, right? Sure, I mean, computer vision is about the camera and all of this rays, but really very much computer vision is about understanding the world out there, like extracting semantic models, 3D reconstruction, video prediction. And if you want to predict videos, you need to start understanding physics or start understanding cooking or start understanding whatever, like human interaction, all kinds of things, right? So I think, you know, a very interesting aspect about computer vision is really it's actually a science, or to some degree, a lot of a science about the world out there. And not so much about the camera, the thing. And I wish one would, you know, see robotics in a similar way. You know, the robot is a bit like the camera. It's just a piece of hardware, you know, that we use to interface and interact with the environment. But the real interesting stuff, really, in robotics is to understand how you can interact with the environment and understand the environment, right? So from that perspective, you know, this is what I find interesting really about robotics. Not so much the robot itself, really, but very much like how the environment works, how it can interact with it. And that reminds me, so just one comment. Actually, if you look at modern like robot learning conferences, there is one called Coral, which I find really interesting, important. There's many papers nowadays, and this is growing, where more and more computer vision people actually go to robotics, and the interaction is better than earlier. Because 10 years ago, it was only like the computer vision people were supposed to do pose estimation, and then there is a software interface, and then the roboticist says, give me poses. And it was like a weird kind of thing. But nowadays, it's really that many ideas from computer vision truly are kind of like interacting and being used in robotics. And why is that? And I think that's a good development. That's because in robotics, people start thinking more about manipulation, and therefore they make everything image conditional. You now have image conditional controllers, image conditional, whatever, grasping, and all of this way of how you can make strategies, policies, controllers image conditional really is a lot influenced by computer vision. And it's all about eventually understanding, interacting with the environment. Okay. So that was kind of like a brief introduction why I find planning interesting, in what was kind of like my view on what I find interesting about robotics. And now here's a couple of examples actually of interesting like interactions. So this is more than 10 years ago. This is a bit more recent. This is an own work some years ago. This is also an own work some years ago. Details don't matter so much. What you see is there's like robots doing stuff, like doing complicated manipulations, right? I'll show a couple of more videos like that. But some of them are like, I think, really quite complicated. Like this one here, this actually goes on really long. This is really a classic. It's very cool. And so far it's only about the robot, but he will also like start manipulating things in a second. All of that stuff is actually purely model-based planning. And if you want to put it like that, it really is generating all of these stuff from very, very little equations. So from very, very little like basic, assumptions. Okay, to eventually talk about my own work, I will have to like introduce a bit like a formalism of how I think about these kinds of things. Because eventually, my research is about trying to understand like scientifically understand, but also, understand these kinds of problems, how you can interact with the environment, manipulate the environment in a complicated and sequential manner. And you've seen the videos, and the question is, what is the right formalism to even start with, right? And many people coming from machine learning would say, oh yeah, it's a Markov decision process. Everything's just a Markov decision process. And that's fine. You could put it like that. And then, the problem becomes one of reinforcement learning or other kinds of methods, value iteration, whatever in a Markov decision process. But there is also a much more structured ways to describe what is happening here, actually. And this is one very structured way to describe what we've just seen on these videos. So this is like a framework, if you want to call it like that, of thinking about these kind of behaviors, and is writing these behaviors down as an optimization problem. Okay, I don't want to like go too much into the details, but I need to make you understand why this is all about these constraints, and this whole talk will actually be about constraints. So the way that it models these kind of behaviors is to say that in principle, these behaviors are an optimum of some optimization problem, where we optimize a path, and this is actually the path of all objects and the robot or so moving. So this path here is x, this little x here, and it's a path, so it goes from some time coordinate to the full configuration space of that scene. And we have some control costs. That's actually the boring part. That the interesting part are the last two lines, and they say that this path has to fulfill certain constraints. What does that mean? So for instance, if you decide, and these are the discrete decisions S, I'm not talking much about that, but if you decide to touch that object and want to push that object, then there is a constraint, a geometric constraint that you need to push it. Or if you decide that one of the objects in a phase is like flying, then on this object there is a constraint, namely that it has to fulfill, from the point that I release it and then comes down, it has to fulfill like some physical equations. That's another constraint. Point being is that these whole things can be described as constraints on the path of the world. Maybe that's enough to say. Here's a couple of more examples. All of these are like examples for that mathematical program or optimization problem that I see. The point that I want to say is that really some people look at these videos and think, oh, there is some simulation happening here. I see a simulation. My point, this simple point that I wanted to make, actually, these videos are just renderings of that path that I just defined. There is not really like a physical simulator happening here. These are literally renderings of that X path that I just defined on the previous slide. And if you think that these paths look physically okay-ish, then that means that I implemented and coded the right physical constraints so that if the optimizer solves for these constraints, they look like physically plausible. Okay? Okay, I hope you got the gist of this, right? So this is like describing all of these behaviors in kind of like a constrained formalism. And eventually now for this talk, of course, I will go to that. I will go to the point in asking, but how can we do the same stuff, but without assuming that we have perfect understanding of physics and perfect understanding of the scene and so forth, right? So can we somehow do the same kind of stuff, like generate these very complicated sequential manipulation problems without, with learning? What is the opportunity to learn something here? Okay. Here is like I think a crucial like slide. Didn't I? Oh yeah, that one is the first. So this is again about the same mathematical program. You don't have to look at the equations here. Maybe the picture is much easier. So eventually you describe the behavior, like the sequential manipulation, as a path optimization problem. You try to find that path. It's stupid that I used the notation psi. This is the same as x. And it's a path subject to some constraints. These are running constraints and some kind of like waypoint constraints is all right. Instead of doing this whole model-based planning, what could I learn? Well, you could learn the policy. Meaning that instead of doing this whole planning stuff that I just showed, you could learn a policy, which means that in every situation of the robot could just predict the next manipulations, the next little 2 seconds or so of motion. And that's a very, very popular approach right now in robot learning, in robot, like in the community. And actually these policies are very often like, because the training data is very often multimodal and there is often very different options of what you can do in any situation. Actually, there is something called diffusion policies, which is exactly that. So given in any situation and given an image of the environment, predict the next 2 seconds. Was there a question? In that case, the policy is a neural mapping, like a generative model, really a diffusion process that is conditional to images. So you imagine literally the robot has a couple of like cameras, 4 or something like that, and it outputs, it generates the path, the robot path typically for the next 2 seconds. And that diffusion model is the same, and it's being queried like with some frequency, with 10 hertz, it's re-evaluated and so forth. Yes, usually faster, but it's predicting again and again and again, yeah? Yes, it's trained once, usually with behavior cloning, but it remains the same. Okay, so this is a super like popular thing right now happening in computer, in robot learning. And here's the other thing you could learn. And this is what I'm going to talk about, because instead of like learning a neural generative model of the next 2 seconds of behavior conditional to images, you could also learn constraint functions, like neural constraint functions, right? The point being is that in all the previous like little videos that I showed, these constraints functions, I had to code them. I had to like code what does grasping mean, what does hanging, we will talk about grasping and hanging in a second, what does physics mean and stuff like that. And that's of course annoying. And so instead of that, the view is that what we're going to learn actually outputs the constraints. Okay. And this is, I think, maybe a bit unusual. Maybe it's very specific to robotics people talking about that or so. But I think it's a super important view on what actually policies should do. So typically, if you are normally trained person, like you heard lectures about reinforcement learning, Markov decision process, you always get like in your brain, a policy is mapping from state to action or from state to controls or so. And then you learn about Markov decision processes. And it leads you to thinking in like very Markovian, kind of like small Markovian steps. But actually in this view, actually policies output constraints on the future. And on a fine resolution, that constraint could be a tracking reference, could be like an end effector kind of reference or whatever, right? But on a coarse resolution, these constraints could also be something much further in the future. And these could be subgoals or something like that. So for those of you not in the robotics, think about video prediction, right? You could try to do video prediction by always predicting the next 2 seconds of whatever cooking or so. But if you try to do that, maybe these kind of video predictions are not super long-term interesting. But if you try to organize video prediction differently, I don't mention certain work, but somehow enforce that is actually like predicting a bit more long-term sub-goals or like crucial like things, waypoints in that video prediction, actually the predictions can like generate much more longer-term interesting like behavior. much more. Like for cooking or so, you predict like it will grasp the knife and then do like many long-term stuff or so. Okay. But in any case, if policies output constraints in the future, then, there is always a controller that actually translates that to motor controls. And honestly, in robotics, that's always the case anyway. There is always eventually a controller that computes the motor currents or something like that, either with a PD controller or something like that. So in practice in robotics, it's always like that. And policies just give some rough constraints in end effector space or even joint space or so for these controllers. Okay, going back to the sequential manipulation planning. In this mathematical description of this manipulation that I showed earlier, which is called LGP, Logic Geometric Program, I said it already, like these constraints are usually ad hoc defined. I defined it and it assumes perfect model, but we can equally give just some neural functions as constraints. And these functions could be image conditional functions that define these constraints on which define that optimization problem. And really the solvers, I use very classical solvers like optimization methods, augmented Lagrangian, not so important what kind of solvers I use, but actually these solvers don't really care whether it was me coding these constraint functions or whether these constraint functions are some neural functions, as long as they're differentiable and nice, right? Okay. Totally. This will be all about, the next section will be all exactly about that. This was kind of giving the background. Right. So this is the bigger picture, let's say, of what I'm actually interested in. And now I'm going to give one particular specific technical example of how to actually do that. Okay, but you get the point. Instead of framing the learning problems within sequential manipulation or robotics as a low-level policy or controller learning or reinforcement learning or so, here it's really been framed as learning the constraints conditional to images. And if you learned these constraints conditional to images, you can use the kind of computational processes, planning and reasoning, as I had before, on top of these. Okay. So this is the paper I kind of picked as the technical part of the talk. Danny Dries was a PhD student with me, super successful, and he's now also West Coast in some startup. He was with Google after that. I mentioned also another paper, maybe at the very end, that Danny Dries wrote, which was about language models and super fancy cited. I don't know what. But before he did the fancy language models, he did that cool work. And I wanted to talk about that cool work instead of only the language model stuff. And he did it together with actually Jung-Soo Ha, who was a postdoc in my lab. He's with Tesla, I think now, doing autonomous driving, something like that. Anyway, so these two led this kind of work, and it's called Deep Visual Constraints. And this is a bit repeating what I kind of said already, but in principle, this you will see in a second a couple of videos where the robot picks up a mug, and it's going to be different mugs of different sizes or so, and it has to pick it up and then move it and then hang it on this hanger. It's pretty small, but I hope you can see it. It's like this wooden hanger. It's funny how many papers in robotics are with that hanger. There's 20, whatever, or no more, maybe 40 papers that use exactly that hanger and do this, hanging a mug on the hanger became a thing, kind of. We were the second. There was somebody before us. Anyway, so, okay, picking the mug and hanging the mug. How can you learn that? You could, frame reinforcement learning like microscopic policy or so, or you could learn the constraints of picking and the constraints of hanging and then use them in, the control framework that I showed earlier. So, how can we solve or do this thing? And that's another thing, only based on images. So without actually having a model at all about the mug. So this is not in our model. There is no thing or so. And in a sense, also without, a model of what hanging, what the hanger looks like. So the answer will be that we learn these constraints functions. I said that one, two ones, one for what is a good grasp, one for what is a good hang. Sounds funny, a good hang. And then once we have these functions, we use the planning methods, really. So the optimization methods, with those on these neural constraints, solving for, the the poses that actually do it. Okay, so here's how we do that. When was the paper actually? 2021. Okay. Because nowadays everybody would immediately say, why do you use this and not a transformer or something like that? Anyway, so maybe nowadays you might do it a bit differently. But let me now explain like a bit the technical approach. So for this to actually be efficient, we want to train image conditional constraints, but one image is a bit too little. Because if you only have one image of a mark, it's not so clear whether you can learn good graphs, and one perspective is hard. So you should at least have two. Here we used 4. Okay, so we actually assume that we have 4 different cameras from different views, and they're installed above the table. So we have 4 different camera views, right? And what we want to learn is a constraint, and actually the constraint function is a constraint on the relative pose. This is already, typical robotics kind of like thing that Chang-Soo Ha, he kind of like thought, oh, learning a constraint over the robot joint angles, that's annoying. I know kinematics. I know kinematics is the, understanding of how robots move. I know that. I'm just going to learn a constraint about the relative pose. So I'm going to learn what is a relative pose such that if I close the gripper, I will grasp the mug, and what is the relative pose between mug and hanger such that if I release it, it will hang. Okay, so it's just constraints about relative pose, and the rest is obvious robotics like 101 kind of to do. And now comes an interesting thing. How do you actually represent objects generally for manipulation? That's a tough question. There could be a million answers. The classical ones would be meshes, point clouds, sign distance functions. They would all be like maybe model-based. More neural ones would be maybe as a nerve. I will also have an example with a nerve later. Or something different. There's also descriptor fields, more like 3-dimensional fields. And actually here we use a field representation of object. So if this would be an object, we don't represent it as a mesh or something, because we need to learn it in a neural manner. We actually represent the thing as a field, and the field is a function over 3-dimensional space, which represents some stuff, features of that thing. So far, it's pretty undefined what it really represents, but I'll explain in a second. So we represent objects, in that particular case, the mug, as a d-dimensional field. And d, in that case, I forgot, but let's say it's 8-dimensional also. I think it was 8-dimensional, but I actually forgot. Not so super high-dimensional. Okay, and how is that field generated? It's actually a pretty structured assumption that you make about how this field, the 3D field about this object, is defined. How? You assumed, so for every image, you pipe it through a U-Net. This is here. Every image is piped through a U-Net, which, compresses the image, uncompresses somehow the image. And then you only pick one particular output coordinate of the output of that U-Net. And that's the output coordinate, which corresponds to the positional, like the 3D space where you want to query that field. Because eventually we want to query that field at different points. I'll show in a second also. So this is like this particular, a particular output coordinate of that U-Net. And in order to know what this output coordinate is, we actually need also camera calibration. So that's also a robotic thing. The cameras were calibrated. And then this output features at this particular point of the U-Net go through another multilayer perceptron. These are like these little things here, multilayer perceptron. And that defines a 3-dimensional field over the space. Okay, so far it's just an architecture. It's not really defined what it really predicts. I'll come to that in a second. But once we have a field, for instance, about this object, we will now query this field at various 3D points which relate to the pose. And then, these queries of the field, they define features, and we again pipe it, like merge them all through a multilayer perceptron. This is what's here. So we query it at k different points, go through a perceptron, and then require this to be the constraint function. Okay. Maybe to elucidate a bit more. First, the query points, I think I like the thing. So if this is a field and I want to make a prediction whether this is a good grasp or not, a good idea is to query that field at relevant points. And these relevant points, they might be points that relate to the gripper. And here's an example, right? So these are like points that are relevant for deciding whether the field basically is graspable or not. And this kind of like shows, in order to define the gripping, like the grasp constraint, I'm querying that field at exactly these points, and this is predefined. Or if I want to predict the hang constraint, whether this is a good hang or not, I have to predict how these points interact with the field of my object. Remember, that would be cup with a little handle. And so I queried at exactly these kind of like points. Okay, so these are these query points that we have. And now, finally, about how do we train that field that is eventually supposed to represent anything relevant about the object, so that I can predict whether it's a successful grasp or not. The answer is that it's very useful to train it on multiple things. So that field representation of the object, if you only train it to have sufficient information for grasping or only sufficient information for hanging or so, doesn't generalize well. It generalizes much better if you train that field to have sufficient information about many things you could do with that. And so this is called a multi-head prediction, right? So which means that we want to train a field representation of an object from which you can predict many things. And one of the most generic things you could predict is actually the sign distance function. I think people know what sign distance function is. It's easy thing. So it is literally just, the distance to the object, or if I could put my finger inside the thing, then it would be negative, the distance to the object. So it's the sign distance function, right? So that's, I think, a minimalistic kind of idea of what the field that I'm training to represent the object should at least kind of like be able to predict, right? The distance to that object. And if I train that field to at least be predictive for the distance to the object, at least it has all the information about the geometry of that thing, because the sign distance function encodes all the geometric aspects. And that's a bit like a pre-training. And this is super cheap to generate tons and tons of data. So for this one, training the field to represent the sign distance, we can generate like really, I don't know, millions of data points. That's cheap and that's cool. But we, in parallel, like really as a multi-head training problem, we also train that field to be predictive of whether this is a good grasp or whether this is a good hang. So it should be predictive for all of these three things. And for the first one, it's super cheap. We can generate lots of data. For the other ones, generating the data is much more expensive and we don't have so much data. We literally, in a simulation, test many, many grasps and just randomly grasp and check whether it's a stable grasp. And that's the data which we use to train the grasp classifier, the constraint classifier. And same thing for hanging. So this is like really training, doing trial and error in the simulation to generate the data to train the the constraint function for grasp and for hanging. So in that sense, it's really a bit like trial and error in simulation, a bit like reinforcement learning. But what you extract is not a policy, but just the constraint functions. Yeah. Well, what we train are these like multi-layer perceptrons in the UNet. Yes. So the UNet and the multi-layer perceptron together, they define this field. I hope it's clear. Like the object is represented, like a field, like a cloud, or I don't know how to express it, but it's the field is defined over the full three-dimensional space. Yeah, but it is only queried very locally. The query points only locally queried. And the local query points, they define the features for which to actually make the prediction of sign distance function or hanging or grasping. There was another question. No. It really relates back to that kind of like thing. Like, it's really, we learn good grasp, good hang. And the in-between, in that case, is just control theory, really, because we understand how the robot moves. It's again that kind of like thinking, we understand the robot, that's the boring part. We know how we can make it move. The interesting part is all the things that are hard to understand, the interaction with the environment. no, but actually what we are learning is only the grasp constraint. It's not the neural system here does not predict one particular grasp. It only implements a constraint function, a differentiable constraint function. And so it's actually the controller that, given that the neural model knows what a grasp is, but the controller will choose the optimal grasp from all of the ones that fulfill the constraint, right? So it's not just, you know, predicting one grasp. Okay, cool. How am I with time? I think I forgot time. Okay. So here's examples. Let me first do this the simulated video. The quality is not so great if it's that large, but these are the training simulation. So this is in simulation. I think the objects, they also look a bit, I don't know if you can see it, they look a bit weird. And that is because we had to convex decompose the meshes. They don't look so high and nice, but if you do these physical simulations, you usually have to convex decompose the meshes. So just to make the simulation more efficient. And there was lots of trial and error to do the hanging and also the grasping. And there is like more. Anyway, so this is how we generated the data, trial and error of hanging and grasping. Okay. And then once the constraints are, can I close this? Once the constraints are like learned, it just executes that. So the video is actually a bit boring. It just grasps and hangs. Okay. And that was for one cup. Does it for, is it the same cup? I forgot. And then later does it for another cup at a different like thing. Okay, it's not so super impressive, but I think it's cool. Okay, there is a ton of limitation. Yes? It's the same neural function that for any kind of images constructs a field, so which is predictive for successful grasp. And you wonder, how could that possibly work for different MUX, right? Well, the answer is that it was trained on different MUX. In particular, it was trained for different MUX to predict the signed distance function. You know, and this is very cheap to compute like that kind of data. But this means that this field representation was trained to, I shouldn't say reconstruct, but to construct a field representation from any 4 images to be predictive for the signed distance. So it actually also does shape reconstruction implicitly. But we don't use the shape reconstruction part, we only use the grasp prediction part. Yeah. Yeah, let's talk offline about probabilistic. Yeah, okay. Limitations. There's like, there is a ton of like limitations. So first thing, and this is something, so I really love that this example, how it exemplifies my idea of, which I find is super promising to learning these constraints and can generalize very strongly because it can be combined with classical planning. But the constraints are actually object class specific, and also the field representations, these trained object representations are very class specific. It works only for MUX. And I find this super annoying, I must say, because it shouldn't depend on whether it's a MUG or not, right? It should only depend on the local geometric feature. And I find this like super limiting, I must say. It's not really my super field of expertise, and now it gets completely into computer vision, right? How we can have much more general and stronger generalizing like methods, which are not object class specific or so. And I think it should be really just depend on some geometric features. And I just mentioned, maybe some people know this paper or so, but there is like other kind of approaches that try to predict grasps, and they're not object specific. They're really just, grasp on any kind of point cloud. One is called AnyGrasp. And things like that, I think might be like much more, or, would be much more interesting and much less limited really. Okay. Maybe I skipped that work just for the sake of time. So although I don't have too many slides, but I took some time to discuss. And let me then kind of conclude. So this was one particular like piece of work, right? And I I like it a lot, although it's not so cited so much, it's not so famous or so. But I really like it a lot because it really tries to think about what should I really learn in order to enable the kind of like reasoning mechanisms that are very strong and can generalize very strongly, and represent the environment, in a way that I can still use these methods. Okay, the bigger picture actually is that eventually, I think in robotics and also for these kind of like planning problems, we want to, and I now use this word to trigger some associations, we eventually want to have generative models of behavior or generative models of plans. I think everybody would kind of like agree to that, right? Now you all have like a very specific ideas what generative models are. You all think about the diffusion and flow models like right now, right? And this is actually cool. This is right thinking. The planners that I'm thinking about are also generative models, especially the optimizers. They also like really generate kind of like, paths, just like other like trained generative models. And also the algorithmic processes. Remember when I earlier talked about architectural like assumptions or so? The algorithmic processes of, say, flow integration or like diffusion model denoising and optimization are even pretty similar. They also do gradient descent. Langevin in one case, just augmented Lagrangian in my constraint-based things, right? I find it super interesting to have so different types of like generative models. The one completely model-based using, classical like optimizers. On the other hand, like learned models such as flow models or diffusion models. And I think if like just scientifically, I think it's a super, super interesting idea or question to think about how could this be like reintegrated? These kind of like different ways to think about how can I generate stuff, in our case, behaviors or like trajectories that fulfill constraints either as they were in the data or how they're given like by some kind of model-based planners. And that's my, generic like view of what we really should try to solve. And, this what I just described, learning the constraints explicitly is one approach. I would maybe nowadays actually learn them differently. Like we start also learning them now with literally generative models, but that's a different topic. If I had time, I would kind of like anticipate a typical question that I get all the time, which is, but could you not just learn all of this? Which is like the standard like reply, right? Could you not just scrap all of like this thinking so hard that I do here and just say, just train a language model? Never mind, right? And the answer is yes, you can. And so my short answer is sure, you can, but scientifically it's interesting to also think about other stuff. But let me elaborate. So yes, you can. And the same author, Danny Dries, that worked earlier on this other paper, also has this paper, which is like hell cited. It quickly became my most cited papers, which I found awkward because I know it's a language model paper. And this one literally trains the language model to predict action sequences. So this is like a multimodal language model. It's actually like it takes it takes images, but also image segmentations, also robot joined angle vectors and all of this stuff as tokens into large language models, and then predicts an output sequence. I don't even know if I linked these videos, and then it does these things. You tell it something, bring me the chips, and this is completely like Google work. This was an intern with Google. Bring me the chips, and then it does all of these kind of things. So the same videos that you see like tons and tons nowadays on YouTube, right? Okay. And people like say, can you not use like language models to do all of this planning? And the answer is, of course you can. Yeah, there's no question. I would never deny that. And if anybody is only interested to do a product, like sell a robot that eventually can do it, maybe then that's the right approach, to just use a language model and then it just does it, right? So, but there's like two little comments I would make. So the first is, where does the data come from? And data in that case really meant examples of planning, examples of long-term decision-making, of like interdependent long-term like sequential decision-making. Where does the data come from? Some people would say teleoperation, which I find, again, disappointing kind of. So teleoperation means humans demonstrating it. I would find it disappointing. In that particular paper, that's the part I'm proud of, the data actually came from our model-based planners. Okay, so we do all of this fancy model-based planning and reasoning, right, to generate the data for the language models. And I think that's right. We should be proud of that. Because our model-based planners, they are the origin of generalization. That's where generalization comes from. They have the right priors, right? And by generating so much data with them, we kind of like inherit that generalization to the language models that we train on them, right? That's kind of like my take on that. I skipped the second part. So thanks for your attention, and yeah, open to any questions.
Yeah, thanks, Mark, for this nice talk and really refreshing view as opposed to all these VLAs and big things. It was really nice to see this approach. So we now have some time for questions, maybe 10 minutes. So if you have questions, just raise your hand and Lorenz will come to you.
Right. Okay. I have a question to the last part you described with the language models. So are they actually doing planning, or are they just basically another model-free policy, just with a huge language model behind it?
You're asking me, are they planning? So they predict plans which respect very long-term intricate dependencies. They could do something like stacking towers and first removing the other thing, which if you only empirically, functionally do behavior science, by just looking on that behavior, you would say that's planning. Yeah, you look at it and then you say that's planning. So I would say they do planning. But it's not, they don't do any kind of like internal, like they don't learn any predictive model. They don't learn to predict what will be the effect of their actions. They don't do any backtracking. They don't do tree search as a chess engine. They don't do any of these things that we classically call planning when we were referring to the algorithms, right? But if you just scrap all of this and say, I don't care what's happening internally, I just care what eventually I see, then they do planning, because they solve like really long-term, intricate, interdependent decision making. Language model. They produce probabilities over plans, maybe, right? But there is also some work that, a language model outputs probabilities over the next tokens. So you could also interpret the whole thing as a distribution over actually action sequences or decision sequences, and then filter that with other things. So from all of these possibly predicted plans, then use the ones that are most safe or whatever. Yeah, but this is beyond that work. But other people already extended this to predicting many plans and alternatives. Yes.
Thanks again. In the beginning of the talk, you said that, for example, some machine learning models or also classical tree-based models can generate newer, interesting or weird chess games, etc. My question would be, like, you just said that these models actually don't predict in the normal sense, but could they actually be used as generative models, for example, taking, after learning a policy, setting up an environment according to that policy, etc. And my other related question is, there is also, I'm not sure if you have heard it, but there's also a paper roughly called models, like iteratively developed models that use the data that they spit out themselves. Then they start to collapse. So the idea was that in each step of data generation, these models start to forget some nuances in the data. How is this possible, even though the models are also capable of generating new nuanced examples?
Yeah, I'm not sure if I understood the first question really so much. This was more about, can it predict an environment? Maybe I didn't get this right. but I can just answer the second question. So the second question is an interesting one. You were referring to the paper when I think I'm not like super familiar with the paper, but if you like train a diffusion model on some kind of like real data and then use that learned diffusion model to generate like new virtual like sample data and then train the next diffusion model on that sample data, right? It eventually collapses. Well, what I think immediately is I had a time when I was working in my PhD, actually. I don't say how long this is ago. I worked on evolutionary algorithms, and actually they're cool. Like they're just also really more theoretically grounded evolutionary algorithms, which are really nice. And in that domain, it is very, very often the case that, you take a population, and the population is a sample representation of like good choices. You kind of from that generate a new one, and then you select again and so forth. But if you iterate that process, it actually also collapses because there is too little entropy if you do it wrongly, right? And so in these kind of like iterative processes, what you really always have to ensure in every generation is that you still feed in two ingredients, a bit of entropy and a bit of selection. And in what, this typical diffusion process does kind of like neither of these two things. I think in every iteration, you would still have to impose a bit of selection, like again, some kind of, like an energy function or like a importance sampling kind of like function, importance weighting, maybe that's the right thing, as well as entropy. And I think in that case, I would find it super interesting to have diffusion evolution models, but I don't know of any of these yet. In that, if you would apply this to this whole planning, we were completely away from the planning thing. But if you would apply this to this whole planning, what it actually means is that these like combined generative models and model-based like planners, they become more and more specialized to generate all kinds of plans and learn more and more efficiently to generate all kinds of plans in a physical environment, which I actually find super interesting. And yeah, also want to do research about. Yes? Oh,
Yeah. So the entropy part that you're telling, so you'll introduce filters in that case to the models. Like you'll put some noise and then extract it back to get the perfect results.
Yes. So that's easy. Yeah.
I had another question, it's a bit philosophical, because you mentioned MDP is about time. It uses time as a constraint, like mostly Markov decision processes. Like from what I learned, at least, that they mostly use time as a constraint.
The thing I cannot parse is if you say it uses time as a constraint. What
but
does that mean?
In policy learning, at least, they use time-based learning. Like mostly, in most cases, time is used as a constraint in learning the different paths.
When you say as a constraint, you mean it is input to the policy? Like it's a non-stationary policy?
As a non-stationary
conditional to time?
Yeah, exactly. Yeah.
Uh-huh.
Yeah, but like if you combine both time and space, because now you mentioned that neural constraints, you can use it as space. So can we define it as thinking?
Yes. Okay. Good point. Yes. So, so these constraints, they were the constraints on the grasp only or on the hang only. So they're like super localized in time. They're just one thing, right? But it's super interesting to think about other kinds of constraints that are much more about the spatial temporal structure in solutions. And to take a completely different example, take again video prediction. Right. So there's certain, you could impose in video prediction, if you like train some quantized, whatever autoencoders or so, predictive autoencoders, you could distinguish between certain discrete abstractions that only refer to constraints in a state, but you could also like have some kind of abstractions that refer to spatial temporal correlations, right? So when there is really a very clear structure in the progression of the video, which relates space and time, like flying a ball or something like that, right? And I find this super interesting to not only learn like these purely spatial constraints or like pose constraints, but really also spatial temporal constraints, which tell you that if you want to achieve that, you need to respect, the spatial temporal constraints, like a flying ball, or if you want to throw something, etc. or something. Yes. Yeah. More questions? Yeah.
Hey, thanks for the talk. So what you showed was a motion planning problem, right? Grasping the mug, putting that on the stand. For this, we have traditional approaches like randomly exploring random trees and whatsoever, right? There you have difficult aspects of the problem, which is the grasping part, and then the putting it on the stand part. And what seems to me is that you took out these specific sub-problems, which are especially hard. Finding a solution there takes a long time, long exploration. And for this sub-problem, you just train your representation there, your constraint representation with the fields, such that you don't need to plan there. You just get out like an idea of what is a good grasp and what is a good hang. And then you only need to do the planning in between those. Is that so? Is that, could you say, okay, you subdivided your problem into subparts, and for some subparts you use this training method, for the others you still use traditional planning?
Yes. So I'm happy with how you describe it. Yes. So it is actually true that sometimes for the, to actually find motion between these predicted constraints, we sometimes actually also call an RRT. An RRT is like a complicated, not so complicated, but it's a classical robotics kind of like planner that can find weird paths or so. In all of these cases, it's much simpler because like these smooth motions, you can write down a simple squared optimization problem and it's like, solved, right? That's also why it would be so boring to learn something for that, because it's so simple to, solve these least squares problems. But yes, good description. Thank you.